Tonight we'll begin our discussion of real database design with looking at the different ways that we can construct graphic pictures of our database. One thing I'd like you to remember as we're going through this is that tonight is just an overview. The actual details on how we get down to designing specific database attributes will start in Chapter 3 and run through 4 and 5. So don't panic, sit back, relax, learn about what we're going to be doing in the next several chapters. Two terms you need to keep in mind. One is a data model. The key here, graphic or complex real-world data structure representation, very often done graphically. The other is model, and when we refer to a model and talk about databases, we're talking about an abstraction of a real-world object or an event. So both of these help us understand the complexities of the data and the environment that we're working in. To go a step farther, let's take a look at this.
Hi there, my name is Michael Fudge, and welcome to Conceptual Data Modeling Explained. Are you confused by conceptual data modeling? All those funny terms like entities and attributes and cardinality and diagrams and one-to-many and required and weak and identifying blah 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 blah. Well, I can help you. Conceptual data modeling is a visual representation of an organization's data semantics. I'm talking about things such as what you need to store, like customers or maybe products or orders. And the characteristics of the things you need to store, like customer name, address, and phone, product name, price, and quantity, order number, date, and total. And the data requirements of those characteristics, like the phone number is required, or the product name is a unique value, or the total order is a calculation. Then there's the business relationships between the entities. Things like customer places order, and order appears on product. And finally, there's the cardinality or degree of relationship, such as customer places 0 or more orders, order is placed by one and only one customer, product appears on 0 or more orders, and order contains 1 or more products. After we collect all these data semantics, what do we do with them? Well, as the old adage goes, a picture is worth 1,000 words. So what we're going to do is we're going to end up drawing a diagram. And this diagram is called a crow's foot entity relationship diagram. So let's go back and take a look at our example again, crow's foot style. Remember those things you need to store? Well, those are called entities. We have entities in this example like the customer entity, or the order entity, or the product entity. Remember those characteristics? Well, those are the attributes of the entity. So each of these entities is going to have attributes like name, address, and phone for customer, name, date, and total for order, and product name, price, and quantity. Our attributes had data requirements. Those end up being descriptors on the attributes. Descriptors like the phone number is required, or the order total is derived, or the product name is a unique value. Our business relationships end up being relationships in the diagram. These relationships are lines between the entities, like customer places order, product appears on order. And finally, the relationship cardinality defines the degree of the relationships, and that is represented through crow's feet, and these crow's feet appear on the line. For example, we might have customer places 0 or more orders, and an order is placed by one and only one customer. And on the other side of things, we had product appears on 0 or more orders, and an order contains 1 or more products. Now that's it. That was easy, wasn't it? There's not much really to it. But to summarize, entities represent the things you need to store. These are boxes in your diagram. Attributes represent the characteristics of each entity. The attributes go inside the entity's box. Descriptors define the attribute's requirements. These attribute requirements might be required or unique or multi-valued or derived. Relationships are the business rules that connect the entities together. And finally, the cardinality defines the degree of the relationship, such as one-to-one, one-to-many, or many-to-many. Thank you so much for watching. I hope I was able to teach you some things about conceptual data modeling. Thanks again, and I'm Michael Futch. Goodbye now.
Check out the textbook for more information on why data models are important, but think of them as a roadmap. It's getting us from point A, designing the database, to point B, creating accurate information for accurate and effective business decisions. Check out Chapter 2. It'll tell you a little bit more about database models. These should look familiar: entities, attributes, relationships, and constraints, all of which we talked about in Oracle. However, you'll notice now under relationships, we've added 3 more things to consider. That is a one-to-many relationship, a many-to-many relationship, and notice the preferred annotation there is an M to N. M to M is also accepted, but M to N is a preferred relationship, and that's what we'll use in class. And of course, a one-to-one relationship, a direct relationship. Constants, those are restrictions placed on our data, and those primarily concern primary and foreign keys, which we also talked about during the Oracle class. Business rules are really the source of the information that we gather to create effective databases. Now, business rules, business policies, user manuals, and so on are where we can get some information to develop our initial concept for our database. So, these sources include, along with what we mentioned, the company managers. How do they view the business of business within the company policy makers, department managers, again, any written documents that might be available, like procedures, standards that the company has for performance, and any operational manuals that they might use, either to conduct business internally or conduct business with their clients, and that all of that impacts on our database construction. Now, I've saved the best for last, and that is direct interviews with the end user. If you weren't tired of me saying it during Oracle, you'll get tired of me saying it in Advanced Database. You cannot create an effective database and ignore the end user. You need to talk with them. You need to work with them. You're the expert on designing the database, but they're the expert on the information that they need from that database to conduct their day-to-day business. It's a two-way street. As we look at these different database rules and we start to compile the information for our data model, there are some things that can help us through this process. First of all, in those business rules, normally we will have nouns and they will translate into entities. Verbs help us understand relationships, so the verbs are going to translate into the relationship between two different entities or several different entities. And then the thing we need to remember is that these relationships are bidirectional. They go both ways. Sometimes you'll hear that referred to as reading the relationship forward and backwards. Two questions that help us identify the relationships, and you can think of them in these very simple terms. First of all, how many of B are related to one of A? And conversely, how many of A are related to one of B? Pretty simple formula. The discussion on naming conventions is pretty much a review of what we talked about in Oracle. I'd recommend you take a quick look at it in Chapter 2 just to refresh your memory. Now this next slide on the evolution of data models is in the textbook pretty close to the end of the chapter. But I'd like to move it up front to give you a little understanding of what we are looking at and how this evolution of data modeling impacts on how we create our data models today. Now as we take a look at the model, think about the types of database hardware that we had in each of the time frames that we're looking at. In the 1960s, it was hard to represent relationships. What was the hardware we were using? Well, it was heavy iron. It was big mainframe computers. And how do we talk to those computers? How do we store data? We talked to them generally by using punch cards. And how did they store the data? They stored it in a data stream, normally on huge platters, magnetic platters, or on mylar tape. So it was very difficult to pull out pieces of information. It was very difficult to add information to any one file. So in the 1960s, we can say it was very difficult to represent a many-to-many relationship. In the early 1970s, we figure out relational databases, and the sun rises, if you will. This is when SQL makes it on the scene, and we begin the start of what will end up as an object-oriented database. If we think about the hardware that is in use in the early to mid 1970s, we're talking about MIDI computers instead of a mainframe list in some other building or in some other floor of your office complex. You may have a refrigerator-sized computer sitting in the corner, and you're able to access that computer through a keyboard on your desk and a green screen. And you're able to write very primitive queries and draw information from that early stage relational database. In the mid-1970s, we get into entity relationships within those relational databases. A lot easier to understand. We can actually sketch out the relationships between data. And think about the computer hardware that we're using at this point. Now we've got the start of desktop computers, the early IBMs. The early Radio Shack, what we used to call the trash 80s. All right, they're big, they're clunky, they don't have a lot of memory, they don't have a lot of data, but we use them to access those MIDI computers that are in the corner of our office complex somewhere and store data and pull data out. The big change at this point in the mid to late 70s is now we can store those queries that we have right on our desktop, and we can go in and modify them and work with them without sending them out to a computer queue to be processed. In the late 70s, we get into late 70s and early 80s, we start into the object-oriented databases, the Oracles, the DB2s, the huge database engines now come into their maturity, and those are the engines that we're still using today. We get more involved with the development of data models, and we're able to support now complex data objects in a complex data environment. So think of it in the late 70s to actually the early 90s. Our database grows up and becomes an adult. The next big change is right around 2009 to 2010, and that is when huge amounts of data begin to be stored in relationship to the internet and to internet businesses and, more importantly, internet search engines. When we talk about big data and NoSQL, we talk about non-relational databases, databases that are not accessed by structured query language, SQL. Actually, this, in many cases, appears to be a step back to the old hierarchical 1960s type stream database that we saw then. And there's a reason for that, and in a video we'll see in just a couple of minutes, we'll look at that reasoning, and we'll look actually at how NoSQL works. When we talk about a relational model, relationship model, it's good to understand a little of the history of this. Dr. E.F. Codd, who worked for IBM in the 1970s, actually came up with this concept. It's a matrix of row and column interceptions. Now in advanced database, we'll call it a tuple or a tuple, depending on what part of the country you're from. And these are the models that impacted what started in databasing in the 1970s. If you remember back to Oracle and our discussion of database development, you'll remember that we talked about how the data is developed. How a data structure is created is what we are most important or is most important to us. How that data is stored in the database engine and how the database engine accesses that data, we don't care about. That's up to the database engine. As long as it can deliver us accurate information so we can make accurate and effective business decisions, that's all we're concerned with. Again, the relational model goes back to what we discussed in Oracle, and this should just be a quick review for you in Chapter 2 of our textbook. A graphic relationship to refresh your memory. Here are two tables, agent and customer. The primary key under agent is the agent code, and the foreign key under customer, again, is the agent code. So with that primary key of agent code, we can associate a specific customer or a specific group of customers to one agent who is handling their business. While E.F. Codd came up with the concept of data modeling, Dr. Chen in the mid-1970s came up with a graphical representation of how entities relate to each other, and that's called an entity relationship diagram, or an ERD. And this is a graphic representation of the data that we are collecting and how that data relates to any other table within the database. Now, as we talk about these entity relationships, there's some terminology that you need to become familiar with. Entity instance, we've talked about before. That's a row within a specific table. Entity set is a new term. It's a collection of like entities, and how would we generate an entity set? Well, we do that by creating a selection query, which you became very familiar with during our Oracle course. Next is connectivity. How are these relationships related? And think of this, back to a little bit earlier in the presentation, as the verbs that we are pulling out of the business rules and discussions that we're having to help us generate our database. And then finally, the relationships between all of these entities are represented with Dr. Chen's notations, and we'll see those in a second. Two things to remember here. First of all, the actual relationship is represented by a diamond, and that would be where the verb would reside. And so the relationship name is inside that diamond. Now, I prefer Dr. Chen's method of notation. The textbook, on the other hand, prefers the crowfoot notation, and we'll take a look at both of those. This is Dr. Chen's notation for a painter and a painting. And we would read it going forward first, and when we go forward, we start on the left-hand side of the relationship. So we say, one painter paints many paintings. When we read it backwards, we would say, many paintings are painted by one painter. Now, there's a business rule involved here. Can you figure out what it is? If you said that our business rule is that one and only one painter is allowed to work on each painting, you're absolutely correct. One painter, nobody is able to help him create that painting. Now let's take a look at the crowfoot representation of that. And although the terms are all there, you'll notice our numbering is gone. And if we read this forward, in crowfoot, we would read, one and only one painter paints one to many pictures. If we read it backwards, one to many pictures are painted by one and only one painter. So you can see the differences between the two forms of notation. When you're starting out, I feel the Chen notation is a little easier to understand, and as we go along, we may start to use the crowfoot notation a little bit more. But get comfortable with the Chen notation. Now, in the textbook, they also talk about the UML notation, and that's one that we're not going to work with at this part in the semester. We may pick it up a little bit further in. Okay, let's look at another set of notations, a little bit different now, and in this case, we're going to talk about employees and skills. So we have a many-to-many relationship between employee and skills. Under the Chen notation, we'd read this as many employees learn many skills. And if we read it backwards, many skills are learned by many employees. Very, very simple relationship. When we look at it under the crowfoot notation, one to many employees learns one to many skills. And reading it backwards, one to many skills are learned by one to many employees. Again, you can see the differences between the two different types of notations. Fairly simple relationship between employees and skills. All right, let's take a look at a relationship between a writer creating a novel. And let's agree that our business rule says that only one writer can create the novel. So the first thing we would do in creating our Chen notation would be to start our diamond, and in it we'll put the word creates. And then we'll want to look at the left and right side of the relationship. So our noun is going to be writer. That's the person doing the work. And the output is going to be the novel. Now, we're doing a Venn diagram, so our relationship here would be 1 for writers, based on our business rule. And what can a writer create? Well, they can create one to many. Sorry, I've got a little problem here with our tablet. But the writer can create one to many different novels. Very easy to graphically represent. And there, through the magic of stop motion, we have our correct annotation. Let's take a look at another diagram. And this time we want to take a look at a customer placing orders. So we know that our verb is places. And we're going to expand this one just a little more. Tablet is not cooperating today. And we know the left side of our expression is going to contain customer. And the right side is going to contain orders, or an order. Well, we'll get it here. Not quite sure what our problem is. That's supposed to say orders. So, our business rule says one customer can place an order, so we'll have one customer can place many orders, and many orders can be placed by one customer. Very simple. Let's take a look at one more relationship, and I've gone ahead and drawn this one before we advance the slide. And this is the relationship of a child and a mother. Now, we can say a child has one mother, and that would be reading our expression forward. One child has one mother. But this is a unique relationship because when we read it backwards, we're going to change that relationship. We'll have one mother has or can have many children. So going forward, we have one child has one mother, and backwards, one mother can have many children. So just a little different relationship, and this would be how we would make the notations for that relationship as we start to design our data structures. Now, just like we have object-oriented program languages, we also now, since about the mid-90s, have object-oriented data models. And basically, these models or objects will contain the operations. They're really the building blocks for an autonomous structure. And still, though, it is an abstraction of a real-world entity. So as our programming languages advanced in their capabilities, so did our database structures and the ability to store and represent data. Here's an example of an object-oriented database item represented in Crowfoot. We could represent it in in Chen if we wanted to. Notice the object representation on the left and how that is done. The entity is invoice. The attributes are invoice date, invoice number, invoice ship date, and invoice total. Notice also there is a customer and a line item represented there. One customer with the potential of many line items. So you can see how a UML class diagram is done, but let's focus our attention in this case on the crowfoot diagram, and we can look at the relationship between the customer, the invoice, and the line items within that invoice. And the way we would read this is one and only one customer may have 0 to many invoices. Those invoices or that one and only one invoice can have 1 to many line numbers represented. All right, so a one and only one customer can generate 0 to many invoices, and each invoice, there is one and only one invoice, and that invoice can have 1 to many line numbers.
What is NoSQL? NoSQL is an upcoming category of database management systems. Its main characteristic is its non-adherence to relational database concepts. NoSQL means not only SQL. The concept of NoSQL databases grew with internet giants such as Google, Facebook, and Amazon, who deal with gigantic volumes of data. When you use a relational database for massive volumes of data, the system starts getting slow in terms of response time. To overcome this, we could, of course, scale up our systems by upgrading our existing hardware. The alternative to the above problem would be to distribute our database load on multiple hosts as the load increases. This is known as scaling out. NoSQL databases are non-relational databases that scale out better than relational databases and are designed with web applications in mind. They do not use SQL to query the data and do not follow strict schemas like relational models. With NoSQL, ACID, atomicity, consistency, isolation, and durability features are not always guaranteed. Why does it make sense to learn SQL after NoSQL? With the advantages of NoSQL databases outlined above, that they scale out better than relational models, you might be thinking, why would one still want to learn about SQL databases? Well, NoSQL databases are sort of highly specialized systems and have their special usage and limitations. NoSQL is suited more for those who handle huge volumes of data. The vast majority use relational databases and associated tools.
Next, we're going to talk about external models, and there's actually a diagram that we'll look at here in a couple of seconds, but I want to run over the terminology with you real quick. We're going to start at the top of the diagram with something known as an end user view of the data environment, and then we'll look at the ER diagrams. We'll talk about external schema, and we'll talk about the different entities and the relationships, the processes, and the constraints that are involved in this external model. And here it is, figure 2-7 or 2.7 in your textbook. And notice we start at the top of the model relating to our end users. This is an external model. The end users are not interested in anything below the level that they are on. So they don't care how the database was designed. They don't care what database engine is used to store it. They don't care how the data is physically stored. All they are interested in at the end user view is, are we getting accurate info? Is that information accurate enough for us to make good business decisions on. The second level is our level. This is a conceptual model level. This is the designer's view. These are the ERDs and the chins and the Crowfoot notations that help us design that model of data to generate the accurate information. So we're interested in the data here, and what we wanted to do is generate the accurate information for our end user. Now, below that level, we're looking at the database view, the database engine view, if you will, the management system. That's an internal model. We're not really concerned about how Oracle internally models our data, just as long as it can pull up the data that we want and effectively turn it into information. And then down at the physical level, what we're actually looking at is the hardware and software that maintains that data. From our level at the design view, we don't really care what's going on down here as long as that information is always, or that data is always available to us to be able to create effective and accurate information. Now, this model is very effective in helping us understand and really to support our end users. It gives us some ideas of how business units operate and the effect that they may have on our database. It kind of helps us ensure that we've got our constraints in place, they're designed into the database, and really once we apply that external model and everything associated with it, it really simplifies the development of a database application. Again, and you'll get sick of me saying it, we're going for data to accurate information for accurate business decisions. Here's our conceptual model. Again, this is what we're interested in. We don't necessarily want to share this or need to share it with the end user unless they're accurate or actually interested. But at the conceptual model level, remember, we're the pros, we're the ones that are going to design that database to make it most effective. Now, in our textbook, if we didn't have a database to work with, we could use Tiny College. And this is a conceptual model for the Tiny College database that's associated with our textbook. They use colleges, by the way, because you're in a college course, you should be relatively familiar on how a college or university operates. You have professors that teach classes. Those classes are courses and they're assigned to a specific room. What we have left out of this conceptual model is you, the student, but you actually do play an important role. This is a conceptual model for tiny colleges. If we look at this crow's foot representation, the way we would read it is one and only one professor teaches one-to-many classes. All right, if we look at the classes, the class one-to-many classes are represented for one and only one course, or generates one and only one course. And then looking at the room relationship, we can say one-to-many classes use one and only one classroom. Now you may say, wait a minute, how can all the classes be in one and only one classroom? We're looking at each specific class. So a class by a specific professor can only be taught in one classroom at a time. Internal model of our diagram again looks at how that schema is going to be depicted internally in our database engine and the relationship that it might have to any external or conceptual work that we've done. Again, this is all the groundwork that we're laying to get into chapter 3, 4, and 5, where we'll actually start to build these diagrams and relationships. So some of this, again, is background and review from what we looked at in Oracle. Now we'll add the internal model to our tiny college conceptual model, and when we start to look at that internal model, we're looking at how we are going to create the data structure. In fact, we're doing it in really pseudo SQL language. We're creating a table called professor, and there are the attributes that will define our professor. Here we are creating a table called class, and the attributes that will define the class, and so on. Now, we are concerned with the internal model from the standpoint that we are determining how that table will be created. But then where we are not concerned is what our database engine actually does with the creation of that table once we have it accurately reflecting our conceptual model. Right now you may be saying, I am so confused, and that's absolutely natural, totally acceptable. And we'll start to clear up that confusion when we get into chapter 3 next week. Okay, let's take a break, and when you come back, we're going to divide into teams and start work on our database project.